So, well, Dan, this could be fun. So, we have two motors sitting out there. One's a bad motor, one's a good motor. So what I want you to do tonight is test these two motors, find the bad one, find the good one. And it really isn't difficult. It goes all the way back to DC theory, basically, because when you look at a motor, they're really, and both these motors, the leads aren't marked. Makes it even funner. So, because I have experience in the past, old motors where the markings get, to the point where you can't read them. So having some background in how a motor is built and troubleshooting a motor can get pretty simple. And so, here's a 9-lead motor, and this is the way they're laid out. A 9-lead motor is center tapped, just like the way of a transformer. So, the only difference between a 9-lead motor and a 12-lead motor is they're not center tapped. So when you go around the motor, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? I break this center tap, and 10, 11, 12 are in the center tap, right? So it's really easier to wire a motor, a 12-lead motor, high voltage, low voltage, than it is a Y-connected motor. It is Y-connected, right? Just like a Y. I mean, it looks like a Y, right? So that's where it gets its name. Is each transformer, same thing, motor, either delta or Y. So to hook a motor up for a line high voltage, you simply series these two coils, right? The reason for that is I have a larger surface area, length of wire, that I can put more voltage into. If I have half the voltage, I only need half the number of coils, right? So if I took on a 12 lead, say, and I took half these coils and paralleled them versus seriesing them, right? That's how I get from high voltage to low voltage. I either parallel two coils or I series them. High voltage, low voltage. Make sense? And if all else fails, you look on the name tag, I'll tell you. But that's what I say, a 12-lead motor is easier to series and parallel because you take these 10, 11, 12 leads and you hook, 5 would go to here, so you could parallel these guys. So tonight, first thing, we split you guys in half. Half of you work on one motor, half could work on the other motor. Find the bad one and the good one. How do we do that? I mean, how are you even going to find what's inside that motor? Well, look at it. It's nothing more than a continuity test, right? I got a coil of wire, it's going to have some resistance on it. And now that resistance is important because these should all be equal lengths of wire coiled up, right? If I got equal lengths of wire, it'd be like having 1, 2, 3, 4, 5, 6 resistors sitting here in my hand, right? I'm going to stick a continuity meter across one resistor and I'm going to measure its resistance, right? Same thing with the motor. The only difference between a coil of wire and a resistor is DC and AC. When you measure resistance on a coil of wire, it's going to be very low resistance because a coil of wire should not have a lot of resistance, right? So if I wire a motor or transformer with aluminum wire versus copper wire, you think the resistance of that coil is going to be the same? What's a better conductor? Copper or aluminum? What's a better conductor, copper or gold?
Gold.
Absolutely. So if you think about it like that, it's nothing more than a resistor. But once I put AC on a coil, that magnetic field, that changing magnetic field, expanding and collapsing, that's where impedance comes from, right? So that impedance prevents that coil wire from becoming a short circuit. Make sense? So, you take the continuity meter and you grab a wire, don't really matter which one, and you find 8 more wires, right? So, if I grab a wire, it has to be this one, and I grab another wire, it has to be this one, am I going to measure continuity? Absolutely. So, once I find the pair, boom, I'm going to measure some resistance. Mark that resistance down. It's going to be small, but what we're looking for is the bad guy versus the good guy. If all these coils, right, 6 coils should all measure an equal resistance. So I'm going to measure, first I got to find the coils. So once I find the coils, just pair them up. So put some tape up there so at least tape them up. Then the next test I'm going to do is once I find the coils and I've measured the resistance and they're all equal, now I'm going to measure to ground. Because the motor can fail in 2 ways. It can break a coil, right, and not have continuity. That coil can go to ground because the resistance or the insulation in that motor got too hot because of harmonics and melted the insulation. That's why when we put variable speed drives on old motors, you smoke them. Because old motors aren't made with high enough resistance or insulation to withstand that heat from harmonic current. We'll be getting into harmonics maybe next class. And harmonics has become our biggest culprit for overheating equipment. I was just looking at an inverter over at the Sparks Police Station earlier today, and got pretty big coils because it's a 250 kW inverter, so the coils are about that big around and about that tall on the AC side. And the insulation is the material that they use for insulation, like in the old ballast, it kind of looks like tar. And it's starting to drip out of the bottom of one of those coils. And I'm thinking, this sucker's not a lot of life left in this inverter. Because that coil at some point in time is going to go up in smoke. I talked to you about a problem we have with solar PV. I was just working on this Saturday on a site that we lost DC to the inverter. And that's what happened to the wire. Problem is, they use building wire for solar PV. Because the problem we have is when solar was being installed back in 10 time period, most of the solar work was installed by non-electrical types. I've seen working on solar systems installed by roofers, by glazers, by anybody but electrical types. And a lot of it was non-union. And all they had was a single electrician who kind of just oversee the whole thing, and a bunch of just grunts out there bolting panels together, and it's all plug and play, except for the final termination to the inverter. But I see a lot of that. It's amazing how much I see of solar failures. But anyway, so we'll split the class, say right there on this motor, and Hatch can go there and work on that motor, and I'll have to come over and work on this motor. And take a piece of paper or something to write the resistance of those coils on. We have some paper.
Got this whole tall stack of Post-it notes. If they just need a Post-it note and a pencil. There you go.
Okay. So, everybody know how to run a multi meter? Huh? Right, we're gonna run a continuity test. Hey, that's all right for a continuity test. And continuity test. Resistance, open circuit. Right, closed circuit. Open circuit, closed circuit. Right. Sheet grab on these wires. Red one. And all we're looking for is his pair. We got 8 more wires there, it's gonna pair with this guy, right? This is coil. Right? Find the pair, take them together. But you when I find the pair, I wanna mark the resistance. So once I get them all paired up, I'll find the resistance. I'm gonna have 6 pairs in there, right? 1, 2, 3. Actually, when you think about it, because it's only 9 lead, you're only gonna find 3 pairs, and you're gonna find 3 wires, right? That's gonna be common. So is the resistance here gonna be the same as the resistance there? Why?
Because it's going through multiple coils.
So I'm going through 1 coil here, right? I'm going through 2 coils here, it don't matter which direction I go, I'm gonna go through 2 coils. So the resistance should be somewhere double. Right? Right.
We got Joe in class. What's next? 5 and 8.
Look for numbers? Come on. That's cheating.
But it has it on its label. That's
No,
how you
just
do it.
pretend like there ain't no numbers there. Bring them out, because you gotta find the bad one. Even though you might have the pair, it could be a bad coil. Right? So once you find the pair, ring them out, write down the resistance, right? So when you look at that diagram on the board, 3 of them are gonna be equal resistance, and 1 of them is gonna be double. So I'm going from 2 coils.
So, if you're connected to that one,
Makes sense?
go and touch every single lead coming through. Is the tones turned on in the meter? So where it rings? Okay, so that's your pair, you got 2 wires connected to your 2 leads. So then hold on to that one and check all the other ones. So check all the other ones real quick. I wrote it down. You just have to touch it real quick. If it doesn't ring, there's no connection.
2.75.
You just go through all the other wires.
We wanna make sure that we don't have 2 coils connecting with one another. Shorted out internally, because the insulation failed.
So now you have 3 wires that are identified that ring out.
Got it.
Get it?
Yeah.
So if you got
Yeah.
3, you can say, go ahead and take those 3 wires and take those 3 together.
There's your center tap.
Red, brown, and pink.
And read the resistance between any 2 of those 3. They should all be identical.
Yeah, it was.
So those 3 leads represent the center. That's tied together and then comes out on the end of those 3 wires. So now you've got 3 pairs you've got to identify.
Okay.
So you pick a wire and just go check everything, where it rings, and bingo, that's a pair.
So it's like, it's kind of almost like,
There's one or two, one I think.
Almost 58 kilo black.
Yeah, black. That's white.
Maybe my fingers up with them.
Oh, that's also celery. I'm just reading 15.
Yeah, but I don't have any dollars. Right. Yeah, you don't have any.
29. Yep.
We are.
That's what I like to do between these. Only have to do your houses. Yeah. Put all these in the ground? Yeah. Two and two together? One's a blue one. You both of them are? You wanna check one of these to ground? This one, this, should say first.
If you had ground to any of those wires, so basically, yeah, all of those wires,
Okay.
you could group together and go to ground, and it's like, if any one of them, if it rings, well, then start eliminating them, figure out which one
Is going there?
is going to ground.
Okay.
So
the one that's like short, because it's hot.
It's connected to the steel housing of the motor, which is not good. Too much smoke got out.
And so what if we don't fit a town, does that mean that this is the good one?
Well, that means that there is insulation actually between the copper wire and the metal frame of the motor. So, which is good. You
Okay.
do not want conduit
Right in paper, that last one?
from wires to
That's
metal
it,
frames.
zero. So you got 15, this one's at zero. Oh, so this one's one closer. This one's at zero. This one's 3 to ground. You want one again? Or do you want to do one that's bouncing around?
Now, come to think about it, we could sabotage a couple more motors. We could sabotage a couple more motors.
I think you found this one.
It was gifted to us.
31 again.
IME, there's a service truck driver for IME, Robert, and yeah, I told him a long time ago, I said, hey,
This one's zero.
you're doing some neat stuff, Robert, you're finding stuff,
On the ground is nothing.
bring it in.
At 3 to ground.
And he does all the time, brings stuff in,
Uh-huh.
he fixes a motor, brings in a power type motor, brings in a lot of motor control stuff, contactors, and, you know, that all came from the VA. Yeah, so the VA hospital was doing a remodel, and they were just take those out and throw them away. And Paul Davies was on that one, he actually stopped and said, no,
So that's where they came from.
we can use this at the training center.
That's pretty awesome.
So typically, yeah, a lot of my classes, I'll tell everybody, yeah, if you're tearing stuff out, call me up, I'll come pick it up,
How come is it?
drop it by, and,
Why
if I don't
should
want
it
it,
be
I'll discard it. But if it has training value, we need those donations.
Cause it's sending that current, like,
That means the current
to
to the
like,
ground.
going back to the panel, right?
Zero.
Okay.
Because there should be current, or, what's that?
Figure it out.
I think so.
Six to
Come up with
grounded.
solution?
Everything's good?
Huh?
fun sweat bullets over here, so, you know,
Reg-
you did great.
Regular solution over there.
We're talking 36-inch box, but.
Probably leave it at that
Yeah,
mega.
everybody. I
Yeah.
did, and all that. I did.
So, coil one, right?
Eight, seven.
Call that, say, coil one, right? It had what, 7? Coil 2? Coil 3?
1.9.
Yeah, no, I understand. Well, there's,
I didn't even, I don't have any experience in room.
I think there's, so when I did hunter safety.
There's our,
Killing is less than.
there's our troubleshooting wheels,
I don't know if they're tactic.
right?
Yeah.
So, now, you went coil to ground, right? Wire to ground? And you look at it,
Talking and working.
setup. I really only need to make 4 tests. I grab, now that you pair here, you've got
What's a
4 pairs, right? So really only need to test those, any one of those wires, whether it be this wire or this wire.
That's full rest.
Ground.
Just told me he crashed.
I make any one of those 3, 7, 8, 9 ground. Right?
And then they gave him
And the same thing here, so any one of those 4, identify a pair
So the next three ground.
What was that, 5 ground?
to ground, 6 test, right?
This way.
This one up
And now
and
you've
over.
got ground motor, motor's okay. Oh, 30 something hours.
Is a lot of horse.
And I have run into that.
We're good then. I think we're good, bro.
Walk 6 miles.
Not figured that out. The hardest part is pulling it
And
out.
it's like, it's all like, dude, 8 shots.
He's just fixing the
Rubber.
Well, I start figuring it out.
There's $200,000.
I was gonna say five.
Yeah.
That means the ground has.
That's a good one.
Because then if we apply current, they go right to the ground. It could be at the pin, they probably connected the neutral and the on the ground of the neutral, but.
So now, because you got no wire markings, right?
Hey, you like the drink like that?
Now you gotta line this sucker up to a 3-phase.
Those angle shots are a lot harder.
Yeah.
Put on 8-phase.
You're saying,
Oh, little cool stick.
Okay, so.
Nah, no, it is, the fades are different on each side. Look, no, but it's cool, cause you only see what's up ahead.
That's cool
You
stuff.
see that come right in,
The thing before you start here, just grab this guy, and you grab that here, you follow.
Those are the real treasures.
Go backwards.
Yeah, you get out,
Start it, talk to wire.
And then knows how long it's been sitting there untouched.
So, when you tear them out, you're gonna hire.
Why do you charge me? Oh, did you charge me?
They
It's
tell
still
the same
rotating.
That's something to keep back to my grandkid got has on front.
AC is still rotational.
Charging
Swing lines when they're-
I was paid, bro.
Drives that motor.
Because the weird.
I don't know how you fade much, something different, bro. How you fade it like this, one time, and then fade it like this, and then they shot. Like, that fool did that to my homie.
That's their
yesterday.
that's their always all of it.
12 leads, that becomes 10 to 12. So the parallel from the voltage from 5 would go to 11, right? 2 would go to 8. Now that was a pair, right?
All woodpeckers.
But for
Bro, sorry, you can't see here.
90 motor, swapping from 5 to low voltage,
So that.
I'd have to put, drive yourself out.
Yeah, you should joke. For this reason.
Okay, you guys get yours done?
Yeah, we think
Bring
it's a
your
bad
results.
one.
So, what's your first one, 4 coils, right? You have 4 measurements,
It's
Yeah.
easier to make it.
right?
So.
You start with number 1. What's your measurement?
47, we got 3 mega homes.
Because you can.
Let's see what they're saying.
Wire it in parallel or
Yeah, we're getting caged.
Ours was all over the.
Really?
Yeah.
That sucker's not in good condition, is it?
No, not really.
Cause they got 7 ohms, 8 ohms, and in
Because
the
or.
Ah, what do we suck?
center
Get the
tap,
bad motor.
you're gonna double. So they went from 7 ohms to 15, cause you're measuring from here to here, 2 coils. It don't matter whether I measure from here to here, here to here, it's still 2 coils, right?
Whereas if it were.
So,
The other way.
to measure the ground now, I would have to take 4 measurements, right? If I measure here to ground, I've covered both of those. I don't have to measure this guy, I've already measured
So
it,
that
right?
is
Same thing here, same thing there. I can measure any one of these to ground,
And they're starting to make the same.
it'll be the same thing. Cause if I'm going to ground and I'm measuring here, and I'm going to ground over here somewhere, it doesn't matter whether it's here or here, I'm still gonna measure the ground.
So 7, 8, 9 should have the same, their arc and.
I'm just going off of when I.
Is there a chance they don't?
Cause there's a center tap inside the motor. Now, if I remove that center tap, it becomes a 12 lead motor. A 12 lead motor is really easier to wire up. To parallel that, I simply take pi 5,
Yeah, he made
11,
me
82. I parallel those coils, I can put half the voltage on.
Oh, you were there with him?
Yeah.
I series those coils, I can put double the voltage on, because they're twice as long.
I think it was 9.
Pretty neat, huh?
So if it's a series, you connect 5 and 8?
Yep.
I can't, I wanted.
Because I need twice, I'm putting
Yeah,
twice
they
the
were,
voltage.
they had the nice
If I'm going 480,
Okay.
Yeah.
I gotta have twice the bullet number of coils for that 480 volts.
Yeah.
And parallel it, then I can go to 240.
240, 240.
You have the same resistance.
208, right? 3 phase.
Yeah, 280.
And since they're parallel, they're gonna be the same
Yeah.
voltage.
If you're in a delta system, and a lot of pumping stations will have delta systems, delta transformers, because they don't need 277, they don't need a neutral. And then if you're in real trouble, they do a open delta with 2 transformers with a stinger leg, you can't read nothing to ground. That's killer trying to troubleshoot inside of the pump station. Okay. Anybody any questions? Come on, figure out?
Going to, they called me at Eagley Pro, they said they're shooting right. I said, the PM hard, I think our transformer came up there, the mortar came up there. I think it took the code. Hey, when are they gonna offer the Roman spending class?
So, I made some handouts based on our last class. Basically, what I want you to do here is trace, we've got a ground fault condition. And 2 examples. Trace every flow of current in that ground fault. Now, I don't know if you realize it or not, but the utility company does not pull a ground wire in from the utility transformer to the point of common coupling, which is the main switchboard where the meter is, right? They do not pull a ground wire. They pull 3 phases in neutral. Why? Pretty simple when you think about it. You got the utility transformer sitting out here, and they drive a ground rod, and you got the neutral connection going back here to the main switchboard. Neutral bus. In the main switchboard, we've taken the ground bus bonded it to the ground bus. Right? Out here in the field somewhere, I got a ground fault. Phase conductor. We'll call it A phase. And ground. That sucker goes to ground. What it wants to do is get back to its source. So it's going to come back here because this panel, this phase comes back to this panel, and the ground comes back to this panel, and sure enough, the resistance between here and here is going to be, can be pretty high. But once I hit that ground, hits the ground bus here and flows back on the neutral here, that's a whole lot less impedance path for that ground fault. That's why the power company doesn't waste the money to pull a ground wire from here to here, because it's already tied by the neutral wire. Because the neutral on the utility transformer is going to be fairly small. That's why the conductor that they pull for the neutral is always half the size of the phase conductors. Because all the unbalance happens on the customer side. So the unbalance is not going to flow out here so much. And so the neutral conductor becomes a ground conductor for ground faults. And that's why they measure in your main switchboard, you're going to have CTs on all three phases and the ground conductor for ground fault breakers. Because what it does, it measures every electron that goes out here has to come back on one of the other phases or the neutral. There should be nothing, zero current on that ground conductor unless we have a ground fault. So once I have current flow on that ground conductor, by that CT that's measuring, it trips the ground fault breaker. That makes sense? Okay. Because one of the tests, an easy test for any electrician, you got all those conductors, feeders coming into a panel. What I do is I take I have a rope CT for my meter. It's a flex CT, right? And I stick it around all four of these conductors. There should be zero current, right? Because whatever unbalance is going to be shared on that neutral. In a perfect world, there should be no current on the neutral, right? The three phases should balance each other out. Because once I go out of balance, I start to affect the connected loads, variable speed drives especially. So if I get further and further out of balance on my phases, I affect the current, I affect the connected load, especially loads with variable speed drives. If I'm more than 5% out of balance on any phase, the current in the motor will increase 10 times. So you burn out drives, you burn out motors with an unbalanced source. So when I test this, one of my quick tests when I walk into a customer, not knowing what I'm going to find, just got to find a problem, I'll throw my rope CT around a panel feeders, not this guy, because if I read any current, we'll call it 1 amp. If I have 1 amp of current, right, it's not being returned on any of these legs, it's gotta return on the ground. That make sense? Because it's gonna get back to the source. One way or another, it's gonna get back to the source. And it's only perfect world is right there. Imperfect world is this 1/8's gonna come back here. So that's a real quick down and dirty test to find out if you've got a problem, right? So I got 10 panels I gotta look at. I got a problem out here at the main. Because I start at the main, I got a problem. Where am I gonna find it? So I got here, got 10 panels. I slap it around here, oh, panel number 10, oh, there's my problem. So now I can concentrate on panel number 10. Okay, which one of you guys, breakers, is the bad guy? Well, you turn off breaker one at a time, if you can. And the problem will go away when you find the bad guy. So, this is just a quick, down and dirty, easy test that you can make with your meters that you carry around all the time anyway. Any questions? All right. Moving on. So, remember the power quality triangle. Pyramid, I guess it is. Power quality pyramid. Grounding was the foundation. Without grounding, nothing else is going to work. So, did you have any problems tracing out current flow on that diagram? It's amazing how many paths of current can flow on, right? When you look at that. So, a low impedance path is very important because that ground fault current is going to get back to its source somehow. And the more somehows it gets back, it's going to use them all. And it could use you if you provide them a path too.
You know what happened to you when you said you grabbed that.
That's right. I'm standing on an air handler, right? I got my hand on the fan section, and I reach up this copper pipe right above my head because I want to put groundwater on it so I can test it. And holy smokes. Well, it was a simple fix. They didn't ground nothing. They took the feeder from the panel to a junction box on the wall. They took the ground and they screwed it to the back of the box. And from the junction box to the variable speed drive, there was no ground wire. From variable speed drive to the motor, there was no ground wire.
And so wouldn't the ground wire fix the problem of it being like energized, but it wouldn't fix what was causing it to be energized?
That's correct.
Okay.
Because you're going to see here shortly why we bleed current through a motor on the ground. You know capacitors, right? You know what a capacitor is, right? Just two pieces of metal with an insulator in the middle of it. Well, that's a motor. You got a rotor and a stator, and they're not connected to one another. But you can bleed current from the stator into the rotor, from the rotor out the shaft, and looking for a ground source. And that's what happens with the variable speed drive motors.
Failed bearing.
And there goes the bearing. In fact, there's a bad bearing that's been chewed up by a variable speed drive. We get into that, we'll see it better. So, the problem we have in our industry right now is surge suppression devices. In this world, there is no equal. Even though the construction documents say, if they do say put in a surge suppression device, they give you an or equal because they don't want to, engineers don't want to necessarily specify a single device. That puts them in too much hot water. So they always have an or equal. Well, that's where it all ends. So, whoops, wrong button. So here we are. We're in the next phase of power quality mitigation, fixing problems that a customer has because he's got all this fancy equipment he's trying to run, and it don't want to run in the building that they got connected to. So, proper grounding followed by effective surge suppression. It didn't just say surge suppression, it says effective, and you're going to see what effective is all about. And it had to be one of the most cost-effective devices you can put in a facility. Again, here we are, EC&M. I printed out, oh my gosh, 4 different documents from EC&M just dealing with grounding and bonding and dealing with electrical disturbances. So when I get magazine, comes in monthly, I get these articles, I rip off the pages, I make copies of them because they're handy information for training.
Are those different types of surge suppressors?
There are many different types.
So which ones last?
You can go to Home Depot and buy surge
Yeah,
suppression.
but which ones last the longest, because they have a shelf life, they can only take so many surges.
There's so many manufacturers of surge suppression, and there's just a big world of different, you kind of need to know what it is you're trying to protect
Yeah.
to do it right. And there's a good reason for it. And the world of LED lighting starts to create visible problems. Power quality before LED days was black magic, snake oil, because you can't see electricity. And when you're having a problem, what's causing the problem? And if you don't know how to test for it, you can't find the problem. Now you throw in LED lights, boom, I got a problem. Lights are flickering, that light's different color than that light. That one ain't even working, and that one died over there, and it only ran a month. That was visible power quality issue. Customer called up, man, my LED lights don't work. You got a power quality issue. What do you mean? You got a grounding problem. What do you mean? You ain't even seen my building. I've heard that so many times. So now we have a visual sign of a power quality problem. So, where do these transients come from? Believe it or not, the customer creates a majority of his own problems. The utility, you know, what can happen from the utility? Well, there's a function that happens just about every night around here, capacitor switching. The power company will bring capacitor banks on in the middle of the night to raise the voltage, because during the day when everybody's stuff is on, the voltage drops. And at night they'll bring capacitor banks on to raise the voltage, so that at the end of the 24-hour period, my voltage was within 5% of what I'm supposed to provide. So the power company covers their butt over a 24-hour period. They don't worry about the 5 and 10, 15-minute periods that this capacitor switching causes. But they do that pretty much daily here in northern Nevada with these capacitor banks. Lightning, of course, you know, that's a no-brainer. And short circuits. When the wind is blowing, I don't know if you've ever seen power lines coming together, and the sparks that come off those suckers. Whoa, incredible. Fireworks. Or somebody hitting a power pole. Tree branches coming across the power lines. will cause the breaker at the substation to trip, and the reset is probably somewhere around 3 seconds. It'll reset the breaker, hoping it'll blow off the branch. If it doesn't, it trips again, and about 10 or 15 seconds later, it'll reset again, power up the line, hoping it'll blow off that branch that's laying across the line. Well, after the second or third time, then they send out a troubleman, because apparently it must be a bigger issue. So those, and you can imagine, you've turned on a cross-line start motor, right? Or you've turned on a transformer, right? You know that big hum you hear when that transformer's turned on or that motor's turned on, that inrush is, on a motor, can be 6 to 10 times its run load. You can only imagine turning on a distribution line, what that inrush must look like. Gee. Well, that's where the 20% comes from. Now we got all this stuff that the customer has sitting inside this building, generating power quality issues. That's why I've always said at the beginning of my seminars, every building connected with electricity has a power quality issue. If you don't believe me, well, wait till you. Why doesn't stuff last as long as it used to? Oh, they don't make stuff like they used to. Well, that's bull. They make it every bit as good as they ever used to. It's just that your connected load sucks. You're trying to run this piece of equipment off of dirty power. Where'd dirty power come from? Well, Mr. Customer, do you have variable speed drives? Yeah. Do you have UPSs? Yeah. Do you have LED lights? Yeah. And now solar power. Oh my gosh. These solar power inverters, solar PV inverters. And I can't wait. In the next, maybe not even 5 years, I was saying this 2 or 3 years ago, and I said next 5 years we're in for some real problems, because all the solar power is being generated, and now they're connecting these gigantic battery banks to them. Whoa, I can't wait, because you're switching AC to DC and DC back to AC, and wow. In fact, Nelson, about, I'm thinking 5, 6 years ago, out at that big generating site outside of Fallon, dug up all the underground wire in that big 250 megawatt solar site out there. 65% of that wire looked just like this. And it was 750 MCM underground cable, and the insulation looked just like this.
Did they use virgin backflow?
65% of the wire was toasted.
Did they use virgin backflow?
They pulled it out.
What's that?
Did you use virgin backflow? They backflow the ditches because the back soils were higher. Same thing
I
happened.
just heard from one of the guys who was working up there.
We had like one local, we had to dig everything up because the virgin soils were higher. For your level down, it's coated. So you're building a transformer every time you ran.
I've got some images.
It just got hotter and hotter.
Some of the destruction I've had to work with in the 12 years I've been working with solar. I've never built a solar site. I've never, other than service, I've never installed new panels, but I have replaced panels that have been broken or burned out. But my only work with solar has been service and maintenance. So, surge protection will not perform properly unless installed in a correct manner. I have not seen one time surge suppression installed properly. And I've seen a lot of systems that contractors have installed surge suppression, but I can't blame anybody because we've never been taught the proper way to install surge suppression. So if we don't get taught the proper way, we're just gonna treat it like another piece of electrical equipment and throw it in there and think it's gonna work, do its job. Well, surge suppression devices have green lights, one for each phase. And as long as those green lights are lit up, sucker's working. Not really. It just means it hadn't burned out something on the inside. Surge suppression is a sacrificial device. The MOVs are a sacrificial device because each time it hits, a transient hits it, it takes away some of its life because it provides a short circuit for transients. So each time that short circuit occurs, it takes a piece of its life away. So the MOVs have a fixed lifespan. And that's why every manufacturer that I've run across, the best one is Eaton right now, has a 5-year warranty on their surge suppressions. 5 years. Really? I wonder why. What happens after 5 years? Customer piece of equipment blows up. Well, crap, why'd it blow up? We got surge suppression there. I was at the Army Guard in Vegas. 2 big surge suppression devices sitting on top of the switchgear, one on top of normal power, one on top of emergency power. Got up there, opened up the can, both of them are burned out. And they wondered why their IT wasn't working. So, you can't have excess wire on your SPD. You can't have tight turns, like us electricians, we like in our panel, we like nice tight bend, we like the 90s, turn it into rigger. You look back, whoa, ain't that pretty. Yeah, it is pretty, but you gotta treat it like transmission cable, high-speed transmission cable, gotta have radius in it, right? Your communications cable, you gotta have a certain radius in it. You don't see them bending your internet cable with 90s in it. In fact, there's a demonstration we used to do with a piece of telephone wire. Put a nice tight 90, put it across a capacitor, a charged capacitor. It'll blow a hole right through that 90. So there's a secret to success, short and straight. And the lead length adds between 15 and 25 volts per inch of lead. What the hell does that mean? Well, most surge suppression devices on the market have a 1,000 volt clamp, call it. Which means when that transient comes up here and hits that 1,000 volt mark, it shorts it out. Shorts it to ground. 1,000 volts. Ooh. If I add any length of wire to that clamp, that 1,000 volt, at 25, we'll call it 25 volts per inch. How many volts is that in 1 foot? Anybody got a calculator on them? What's 12 times 25? What's 10 times 25? 250. Right?
300.
So 1 foot of wire is going to add somewhere around 300 volts to this clamp. 2 foot of wire. 3 foot of wire. Oh, it ain't long before this sucker is a 2,000 volt clamp. You think you've saved anybody? And I put any 90s in that sucker? Oh, nothing's going to work. So, for surge suppression to work properly, the most important fact is lead length. 14 inches of number 14 gauge wire adds approximately 300 volts to the let through. So if I take a piece of wire, 1 foot, I'm going to add about 200 volts to the clamp, to the let through. 3 feet of wire, it's gone up to in excess of 600. And that's twisted. If take that same 3 foot of loose wire, not twisted, and man, here it is, almost 900 volts. Why do you suppose communication cable is twisted? And if you look at 4 pair of communication cable, each pair has a different twist to it, right? And that's for the purpose of let through or crosstalk, so that communication on one pair is not cross-talking to, say I've got a pair transmitting and I got a pair on the receive side, transmit and receive. If there's any crosstalk between the two, pretty soon you're talking a different language. So, we have different values where we start to destroy equipment. And it all depends on the microprocessor. We used to have, signals back in the old 386 days where the signal was about a 5 volt on off. The on would be about 5 volts, off would be 0. Well, the noise was always much less than the actual computer taught, the on-off signal, the digital signal. But now, with these voltages getting smaller because the speed of the computer has to be faster, we have to squeeze the components tighter together. I cannot have high voltage with my components stacked almost on top of one another. So I had to lower the voltage in the computers in order to get higher speed. Well, now the noise is still the same value, and now the noise is greater sometimes than the digital signal. So now I crapped up my signal trying to get across this building to where I'm supposed to go at the other end. That make sense? So, here's a 100 kW inverter that I was working on, state of Nevada inverter. And this is the current down here, and that's the voltage. The current affects the voltage. So, when I measure a sine wave, right, that is a switching frequency of the engine being the IGBT that converts DC to AC, switches at 10,000 hertz. And I could break that sine wave down from 0 and count the little changes in value, and it comes up to 10,000 hertz. And it affects the voltage. So the voltage now is not a nice, smooth sine wave. And that affects the connected load. So here's dirty power coming into the building from your solar system, creating more dirty power than that already exists in the building. So this happens to come out of the code book now. Routing of surge arrestor grounding conductors. So now they talk about reflected waves. The higher speed of a signal, the greater chance of a reflected wave. And what that means is if you visualize a wave in the ocean coming in, and a part of it's going to come into this nice sandy beach, and it just kind of smooths itself out as it rolls up on the beach. Now that same wave coming in has this great big old rock embankment. It hits that rock embankment, boom, it reflects back. That's what happens with electricity. When it hits the load, at high speed, it will reflect back. So that reflected energy is coming back, and if it's a variable speed drive, and it's sending up 10 to 20,000 hertz over here to drive that motor, it hits that motor, and the impedance of the motor is like a big old rock. Boom! Some of the energy reflects back to the variable speed drive, and can take out the variable speed drive. It will take it out after a period of time, unless you use VFD wire, or you ground that motor, bond that motor to suck out that energy before it's transmitted back to the source. We'll get into that further. So, grounding should be as short and straight as practical. National Electrical Code 285. I don't know if any of you ever read that. I've never seen it done that way yet. So, this is up at UNR. Brand new building, and they kept burning out the boiler controls. So I get called in, and I walk in this electric room, and here's this great big old surge suppression device sitting up here, and I look at it, and the lights are all green. And the maintenance director walked in there, and I look at it, man, this is really a pretty electric room, man. All the normal power stuff's over here at this wall, and the island in the middle with UPS in the middle, and this wall over here had all the emergency stuff. And both normal power and emergency power had one of those great big gigantic surge suppression devices. I said, well, it sure looks pretty, but it ain't working. What do you mean it ain't working? So I took the enclosure apart. I said, okay, we've got 1, 2, 3, 4 90s, and it's coming clear down here. That's about 10 feet of wire. And I says, you've added 2,400 volts to that surge suppression device. So you take the 1,000 volt clamp, you add 2,400 volts to it. You think you're going to save anybody out there? Not a microprocessor, and certainly not the boiler controls. I said, well, you can't blame the contractor and the people who installed it because we don't know any better. We've never been taught any better. I said, had they thought about it long enough, they'd probably put that surge suppressor device right here and grabbed that, put that breaker right there, straight into the surge suppression device. Then it would have worked. But when you lay out electric rooms, you got to think of those things. The surge suppression device has to be the most important piece in that electric room after grounding. So if I'm squeezed for space, like they were here, I'd have to make some changes. I'd have to think of that surge suppression device short and straight. You got a question?
I was just gonna ask you, you like if say called for that on the print that the engineer wrote to put the surge protecting device up there, like was there really anything they could do about it? They had to have that wire that long.
Well, the engineer is going to specify a surge suppression device.
Mm-hmm.
That's kind of where it ends.
Okay.
And it's up to the contractor and his people on the job as to how they lay out the electric rooms.
Okay.
Right? So, we go in there and we've got this big old open room. So, okay, I'm going to put that guy there, I'm going to put that guy there, and I'm going to set it to look nice and pretty. And it does look pretty. Man, there's a nice looking, like there's a lot of space, man. Nothing was crammed up tight against one another. But it don't work. So, how do we fix it? We went over to the boiler because there was no fixing this. So we went over to the boiler and we put in critical load surge suppression devices. A little small device, you put it right at the load you're trying to protect. Here was the other half. Here's normal power. And you think that's going to be a nice radius bend that comes around in the back, and the surge suppression breaker was clear over here. So I can imagine. It might take out a lightning strike, maybe, but that's about it. Here was another one. 20 feet. Here this guy's sitting clear over here. This is what the Army Guard in Vegas. And 20 feet. Well, at 300 volts per foot times 20, oh my gosh, that's a biggie. But here again, we don't know any better. And that's why we put on these classes so that when we get out there in the field, you know a better way to do it. Problem is, a lot of times you're gonna run into a conflict with the general foreman and superintendent, owner. There's a lot of issues trying to do this stuff right, because it costs more. So basically, an impulse is 4 times the peak, 2 times the peak, and ring waves. So there's the different types of transit that we experience. A 4 times peak, well, what's a peak of a 277 volt signal? How do you calculate a peak? What is peak? 277 times what? 1.414 is peak. So that's somewhere around pushing 400 volts, right? So the peak of a 277 volt signal is going to be somewhere around 400 volts. 4 times that, 1600 volts. I've killed a lot of this stuff right here. We've already seen it's easy to exceed that clamp. Very easy to exceed that clamp before I destroy a major part of my equipment. Now I get in a 2 times peak, oh my gosh, that's really tight. And a ring wave, just little tiny guys, now you start dealing with transmission errors. You start dealing with that signal that's trying to talk to, from the computer to the printer on the other end of the building. Very simple. So, I talked about the issue with a generator and a mechanical ATS. And I run across this purely by accident at the VA hospital. They called me in because the neutral terminations were turning red. They were getting so hot. And they said, we have clamped this thing down so tight, we're going to bust the bolts. I said, that ain't your problem. I said, your problem is harmonics. So I put my meter on this emergency panel that serves MRI equipment, right? So here we were, put it on, had it on for a day. They did generator testing every Thursday. So this test happened at 6:30 in the morning. So here we went from emergency power back to normal power, and there's the big old 400 amp copper pads coming together, and they bounce. That bounce creates this transient. Now, at the other end, this load is this MRI equipment that's taking somebody's image, right? The doctor looks at the image, oh my gosh, you ain't got long to live. Kind of drastic, but it's going to affect the image. And it don't happen, I mean, it's not a very long duration, you know, one cycle. And here's where we went from normal power to generator power. Same thing, big old spike. And the generator now is producing a notch. So there's the voltage coming off the generator, and it's got a notch. It occurs every time at the same place. So the generator is not producing nice clean power. But nobody thinks of those things. So that transient went from 175 volts on the top side down to a minus 430 volts. So top to bottom, that's about, what, 4, 5, 600, 7, almost 700 volt transient. Where we already saw back at the little chart that says who am I gonna destroy at that voltage, and if the surge suppression device is not installed properly, we've just added more voltage to that clamp. So the surge suppression device will never affect that. Will do nothing to it, will not clean it up. This is what I see on my meter when I'm doing an analysis on a building. And this particular little transient right here was 2.4 times peak. Well, when we look back at our little chart, what have we destroyed at 2.4 times peak? You know, we're definitely going to affect transmission, data transmission. And this is pretty much what transients look like on a sine wave. EMI and RFI, electromagnetic and radio frequency. RFI radio frequency is somewhere below 15 kilohertz. EMI is something in excess of 15 kilohertz. So depending on what issue you're trying to resolve, you have to find out, okay, which is it an EMI problem or an RFI problem, because there's different solutions for each one. This North Valley High School, went out there, got called in to do a power quality analysis because they were doing an energy retrofit. And in that retrofit, of course, we were putting variable speed drives on all the motors and converting all the existing lighting from fluorescent to LED. So I turned this report over to the school district and says, don't waste your money on putting LED lights in. They won't last. They said, well, you know, talking to one of the maintenance guys, he said, we have a $12,000 budget yearly to change out lamps and ballasts. Already, that's just fluorescent. I said, well, you better double or triple that if you put in LED lights, because with power looking like that, sags, flat topping, so each one of these has its own problem with the connected load. So ring waves has its own problem because based on the magnitude of the ring wave, am I going to affect my transmission? Sags, remember what I said, when voltage drops, it's going to increase the current in a motor, and the motor will increase 10 times the sag of that voltage. And that sag was about 49 volts. Flat topping, what that does is, in a variable speed drive, the DC bus must maintain something in excess of 600 volts. If my voltage coming in drops to a value, how do I get 600 volts off of a 277? Or 480? 480 times 1.414 is what?
600.
Anybody got a calculator?
7 something.
720.
Six, seven, eight.
Huh?
678,
676.
670 volts. So, that's how I charge a capacitor to something in excess of 600 volts. I use the peak of that 40 volt sine wave, right? So I've got my capacitor charged, my variable speed drive is going to operate perfectly. But what if I get a voltage sag? I'm not going to have the 600 volts to charge that capacitor. And the variable speed drive will trip out on low voltage. And if it keeps up, it's going to overheat. And it's going to take out the capacitor, quite likely in the drive, and well, let's replace the drive. Let's fix the problem. Because if you replace the drive, what are you going to do? Replace it again, and replace it again. And that's what's happening in our industry. It's becoming a great big service industry. There's guys driving around with replacement parts sitting in the back of their truck. And this was happening in Vegas a lot. Just waiting for the call so I could take this guy out and put in this new guy. Happens a lot, because a lot of money being made in replacing parts rather than fixing it. State of Nevada, prison systems, 100 kW inverter, got a call, my solar ain't working. Can you come out and look at it? Yeah, I'll come out and look at it. 100 kW inverter, you know, you stand up all like that, open up the doors, it was black inside, it was just black. Oh my gosh, you're right, it ain't working. I closed the doors. So, oh, what can you do? I said, well, if you want, I'll fix it. What, do you think it'd be better if we replace it? I said, well, if you replace it, it's gonna probably cost you $60,000, $70,000. If I rebuild it and you maintain it, probably do it for under $20,000. So I rebuilt it, and it's still running today. But no, they want to replace it. They thought it'd be better to replace it. So we got a 200 volt transient here, we got flat topping going on, we got sags going on, so we're affecting multiple connected loads to this incoming power. And the crap that's being generated in this prison. Have a question?
Kinda, yeah, so you're saying like that's a problem nowadays? The customers wanna replace?
Yes.
They don't wanna fix it?
Well,
They don't want some.
there's an issue with fixing. Some things is more costly to fix, like microprocessor stuff. You can't find anybody that's gonna take a green board and start pulling components out, replacing capacitors, resistors, stuff like that. So I fall into that a lot. But if I can replace it with components that are available, and I mean, I've replaced green boards, control boards in inverters. I've replaced the engines, the IGBTs. You know, there's two of them per phase, one for the positive angle, one for the negative. I replaced those and clean them up, and so it's good service work. You guys want to take a break? So, this is what I was talking about a little bit earlier, about the reclosures that the power company experiences when something hits the power line. Typically, it's tree branches. Something will hit that power line, cause the main breaker in the substation to trip. And it will cause what they call a reclose. And reclose is, 2-3 seconds later, the breaker will reclose, and it creates a spike in the line on the grid. And somewhere around 15 seconds later, it'll do another reclose. If any of these two here don't blow the fault off the line, by the time they hit this third one, if that hasn't cleared the fault, then a troubleman gets called out. So typically, you'll see these events happening during weather conditions, bad weather, windy weather, something. That's why you always see these tree chopping guys always chopping branches around power lines, because these can cause major problems with the customer's connected loads. So here's what an LED driver looks like. That's why we have so much problems with dirty power feeding LED drivers. And they're not a whole lot different between a little LED driver than a VFD. Believe it or not, a motor or a variable speed drive does the same thing, or an LED driver does the same thing as a variable speed drive. Because we're bringing in AC, and it hits this EMI filter, which again is filtering out high frequency, something in excess of 15 kilohertz, and then it rectifies it to DC. Then it hits the DC filter, which is not much more than a capacitor trying to soften up that chopped up signal. And then we got some power factor correction going on. So basically, most DC lighting or LED lighting has a pretty high power factor, something around 97% power factor. And a lot of the old electronic ballasts, same thing, have high power factors. It was built in for that purpose of energy efficiency. So then it comes back to this programmable, and it's varying the voltage sent to the LED lights so it can bright, dim. So the same thing's happening to a variable speed drive on a motor, changing the speed of the motor. So not having a good ground system for LED lighting is going to have problems. And if you ever get a call to a customer's facility because their LED lights are doing crazy things, Mr. Customer, you got a grounding problem. Simple as that. How you fix it? It can be tricky, can be tough, but you got two choices. You replace the light, walk away, come back another day, replace the light again, walk away, come back another day, replace the light again, back and forth, back and forth. It'll never end until the grounding gets fixed. It'll never end. Because these drivers utilize grounding as a reference point. Same with microprocessors, same with every computer in the building. It uses ground as a reference point. That means that ground has to be at the same value. Not necessarily zero, but the same value from one end to the other. It can't be 1 volt over here and a half a volt over there. It messes with microprocessors, trying to either data transmission on your computer network, or these guys here trying to do their job. It just won't work. And that's the biggest problem we have with converting existing buildings to LED lights. Now, new construction, if you're not careful and ground every lighting fixture properly, then you can have the same problem. But especially with older facilities that use conduit as a grounding means, you can expect to have problems. This again, we're back to North Valley High School. Here's a new event that has started to surface. This event called Flicker went away when we converted from incandescent lights to fluorescent lights. Because in a fluorescent ballast you have filtering that goes on and softens up this flicker event. So you didn't really see it in fluorescent lighting. Now along comes LED lights. And LED lights hate voltage fluctuations. Voltage fluctuations, and you can see down here, this is the real power in kW. And you can match every one of those changes in voltage power causes this flicker event. And flicker event, it's a universal phenomena, and 1 is the number they use to maintain flicker, below 1. Above 1, it starts to affect people. People can see it in the lighting. If you're susceptible to seizures, it'll really nail you. But it kills power supplies. That change in voltage power to that driver is going to take out the power supply in the LED lights. And as you can see here, they wanted to convert this building to LED lights. I told them, don't waste your money. I told the school district, don't waste your money until you fix this problem. And during the meeting with the school district, one of the guys that maintained the new high school out at south end of town. Crap.
Money?
South Meadows. No, yeah. Gamani Ranch. Guy says, you know, he says, we keep losing our parking lot lights. I said, yeah, I can understand that. You've probably got a grounding problem, because, like I said before, they drive a ground rod in with the like standard concrete, and it will not be a low enough value to prevent these problems, this dirty power from occurring. And Ham Lights will travel, they just have a world of work just changing out parking lot lights. I see them everywhere. Oh, there goes another bucket truck. Oh, yeah, yeah. See, not more lights. So, now I'm going to talk about the problem we have with surge suppression and the world of there is no equal. So, typical surge suppression has a threshold, and 1,000 volts seems to be the mark that they shot for. And again, these are MOVs that turn into a short circuit when that value is exceeded, and it shorts out that transient. So we have a 277 volt signal, and the peak is, I call it 400 volts, easy for me to think about in my head. So based on where that transient occurs, if it occurs up here at the top, not a problem. What if it occurs down here and has to travel clear up there to get chopped off? So if we run those numbers, that transient occurs down here, it has to travel about 400 volts to reach zero. It has to travel another 400 volts to get here, and we're still about 600 volts away from the chopping block, right? So now that transient travels almost 1,400 volts before it gets chopped off. And we have killed a lot of small microprocessor electronic equipment. You know, motor's going to handle it, big equipment can handle it, but not most of the control equipment is handling this big piece of equipment. And every large piece of equipment is going to have some kind of electronics handling it, something of a low voltage value. So typical surge suppression operates just like this. And so if I've taken out a ring which is 2 times, which is 700 volts, well, ring happens a lot, because ring can happen every time, anytime somebody makes a copy off a copy machine, that blast of current, that bright light, will cause voltage to flicker, which we call ring, because it's small values. Now, if it's moderate 2 times, 785, well, shucks, I ain't even got there yet. So all my moderate equipment is going to get damaged. Major, 4 times, 1,570 volts. Well, by the time I got there with short and straight, you'll never get there, because I haven't seen one installed short and straight. So by the time I added any length of wire to that 1,400 volts gets increased by 300 volts per foot of wire, of lead wire. So I can do major damage with typical surge suppression. Now there is a place for typical surge suppression, and that would be at the main switchboard. Because I'm trying to prevent happening there is lightning strikes and large events that happen on the grid, power lines blowing together. I want to trap these big guys before they get into the building, past the main switchboard. Once I leave the main switchboard, I got to look at better protection. And there's only one manufacturer that I know of in the world right now, and that's Innovative Technology, and Eaton bought it out. This is Innovative Technology. Their technology builds a nice little protective loop around that sine wave. So no matter where that transient occurs, it's going to trap it in that protective envelope. but they're very expensive. These suckers probably cost 3 to 4 times what a normal run-of-the-mill, I don't care who manufactures, Eaton makes them. Eaton makes surge suppression. You pay, I don't know, I don't buy this stuff, but I know they're not as expensive as. Innovative technology is gonna cost somewhere between $3,000 and $4,000. Where your, or equals, will cost maybe $500 to $1,000. Difference is, remember I said, every surge suppressor on the market today has a 5-year warranty. Eaton Technology, Innovative Technology that Eaton bought out, has a 20-year warranty. If that sucker dies within that 20-year period, you just call them up, send them the serial number, and they'll send you a brand new one, no questions asked. So 20-year versus 5-year, that must say something about the quality of the product.
Since it's newer, do they know like the full lifetime of it?
Yep. So if a MOV has a sacrificial life, and everybody else in the market can only handle 5 years, and theirs can handle 20 years, that must say something about why am I paying $3,000 or $4,000 for this piece of equipment? Because it can sit there for 20 years. And I'm gonna protect you for 20 years. But when that other device, it's got a 5-year life, when it dies, are you even gonna know? No. You ain't gonna know. If I start blowing out equipment, crap, why am my equipment blowing out? Washoe County. Transients occurring, transients. They're occurring all the time. There's, I think, somewhere I read that people are buying panels with surge suppression built in the panel, which is not, and I think it's in the Emerald book, not a recommended practice, because how are you gonna repair that? How are you gonna replace it if it's attached to the bus? Surge suppression, and here's 7 of them. This happened to be up at the Western Nevada campus. Probably the only one that's gonna work might be those 2 right there, if they're sitting right next to the breaker inside that panel, short and straight. These other guys, well, they're compromised, but they sure look pretty. Man, they really did a nice job, nice and level, whoa, boy. Did an awesome job putting it together. So, we'll call it a night and move forward with variable speed drives. That gets funner. Any questions on what we covered so far? I have a tendency to go too fast, I know, but so I'm sure can't possibly have absorbed everything.
So for your surge protective devices, I know you said they're supposed to go, was it short and straight? So what's ideal for that?
That's hard.
Yeah.
I'll admit, probably the hardest thing there is to do is get it short and straight. It really takes some thinking out of the box. When you start to install one of those devices, where in the heck am I gonna install it? Sometimes I've had to install them and panels full, breakers full. So what I've done is I've tapped the bus and I put a little 30-amp fuse block and feed the SPD right off that fuse block. So I come right off the bus, put my 30-amp fuse block, fuse holder, right inside, not very big. Feed it right into the SPD.
So to protect that last one, I heard one of them say right now, but like, well, the way to protect that last one, that where all the surge protectors are moving out, and they said it would be like circle around it and close the breaker that it's going to, the closest one.
I'm not following.
Like, cause on the last one.
Can we go put that
Oh,
slide back
here,
up?
on the last one that you showed.
Oh, yeah.
How they're coming this way, and you said these 2 were the only effective ones, really. What did it make it? would the way to make it effective be to have these ones, like on this other side of the panel and hitting?
Well, again, you really gotta think out of the box now. You know, you gotta
So it's
see
not gonna
where
be
it's
like the,
that.
it's not gonna be like the prettiest thing, right? It's gonna, I mean, like obviously what you were saying, you know, like it looks nice when you're putting them in like that, but
But
for it
they're
to be
not
practical,
effective.
yeah,
They're
for it
not
to be
effective.
practical and actually work,
Right, so.
that's kinda look crazy.
Probably what I would do is I would put a large one. I think what they're doing is they're putting one on each circuit. I would put one on the main board, which protects all the circuits, right?
Okay.
Because the transient's coming in, no matter where it's coming in from, this provides a low impedance path, shorting it to ground. So if I protect the whole panel,
You don't have to worry about
then
protecting
all the
the
connected
individual.
loads are protected.
Okay.
But the problem is, we in the electrical trade have never been taught this. We don't know nothing about the fact that I got my computer plugged into this device I bought at Home Depot, and does it protect my computer? I don't know. I never look at it, right? But, you know, we don't know any better. But that's my goal, is to try and get our trade into another level where our technology